Mars, the red planet we have always watched in the night sky, hides secrets beneath its surface. A few years ago, space probes photographed strange holes on the Martian surface, entrances to giant caves that no human has ever visited. These caves can be hundreds of meters deep and stretch for kilometers in total darkness. Inside, protected from the deadly radiation of space, temperatures are more stable than on the freezing surface. This made scientists ask something shocking. Could some form of life be hiding in these caves for millions of years? Get ready to fall asleep while listening to this video and travel to these mysterious tunnels of another world. Subscribe to the channel. Leave your like and comment where in the world you are watching from. Get comfortable and relax. Let's begin. Imagine peering into an abyss on another world, a hole so deep and dark it swallows the light. That simple question opened a door in our minds, leading us to envision a hidden Martian world waiting to be revealed. The caves call to our innate curiosity, our drive to explore the unknown. They are the ultimate closed rooms in the solar system, holding secrets about the planet's volcanic past, its potential for life, and its future as a destination for humanity. Every skylight is an invitation, a challenge. We have seen the doors. The next step is to learn how to walk through them. This initial discovery phase, these eyes in the Martian darkness, have set the stage for what could be the most profound exploratory endeavour since the Apollo landings. It is a reminder that discovery is often a process, a chain of observations and deductions that slowly pulls back the curtain on a wonder. Mars, a planet we have observed for centuries, still holds vast realms unseen. The cameras in orbit acted as our proxy eyes, revealing the first hints of this subterranean landscape. Now, the task is to build the robotic, and eventually human, explorers who can descend into that darkness and turn the unknown into the known. The story of these caves is still in its opening chapter, written in data and shadow, but it promises to be one of the defining narratives of our time exploring the solar system. We stand at the precipice, literally and figuratively, looking into those dark openings, knowing that the true journey is just beginning. The discovery has been made. The path forward, though incredibly difficult, is now clear. We must go underground. So we've found these incredible skylights, these doors into the Martian deep. But what exactly are we looking at when we peer down into that blackness? What kind of architecture could create such vast, hollow spaces beneath the surface of a seemingly dead world? To understand that, we have to rewind the clock, not by a few centuries, but by billions of years, to a time when Mars was a very different, violently active planet. The caves we see today are almost certainly ancient lava tubes, and their story begins with fire, not water or gradual erosion. Picture Mars in its youth. It wasn't the cold, dusty desert we know today. Its interior was hot, churning with molten rock, and this heat found its way to the surface through titanic volcanoes, the largest in the entire solar system. Olympus Mons, period, for instance, isn't just a mountain. It's a monument to persistent volcanic fury that lasted for hundreds of millions of years. During these long epochs of activity, eruptions weren't always explosive. Often, they were effusive, meaning lava would pour out relatively calmly, spreading across the landscape in great, molten rivers. Now, here's where the physics of lava creates something special. When a river of lava flows, the material most exposed to the cold air, the top and the edges, starts to cool down first. Lava is essentially liquid rock, and when it cools, it solidifies. So, The very outer layer of this flowing river begins to harden into a solid crust. This crust is an excellent insulator. Think of it like skin forming on a pot of very thick gravy. That skin traps the heat inside. Beneath that newly formed rocky roof, the lava remains hot, liquid, and continues to flow, completely insulated from the cold atmosphere above. This process can continue for miles and miles. The lava river is essentially building its own tunnel as it goes, a protective conduit that keeps the main flow hot and efficient. Eventually, the eruption event that was feeding this river ends. The source of fresh, molten lava shuts off. What happens next is crucial. The remaining lava inside this long, rocky pipe is still liquid, but it has nowhere to go. So, it continues to drain downhill, following the slope of the land. Pulled by gravity, it flows out the far end of the tube, leaving behind an empty, hollow tunnel. Voila, a lava tube is born. This exact same process happens on Earth, in places like Hawaii, Iceland, or the Pacific Northwest. You can hike into these terrestrial lava tubes today. They are fascinating, but they are also relatively modest in size, typically a few meters to maybe 10 or 15 meters across. This is where Mars takes a familiar geological process and supercharges it into something colossal. And the key factor is gravity. Mars has only about 38% of Earth's gravity. This lower gravity has a profound effect on the mechanics of lava flow and the stability of the structures it creates. On Earth, the high gravity means lava flows are shorter and stumpier, if you will. They spread out quickly, and the weight of the rocky crust can more easily cause a ceiling to collapse while the tube is still forming or soon after. On Mars, with much less weight bearing down, everything scales up. The lava could flow for much greater distances without cooling as quickly. The insulating crust could form over much wider rivers of lava, and the resulting empty tube, once drained, could remain standing under its own weight far more easily. This is why planetary scientists theorize that Martian lava tubes could be absolutely monumental. Estimates based on gravity and rock strength suggest these subterranean tunnels could be 100 meters or more in width and height. Some studies even suggest possibilities of tubes several hundred meters across. To put that in perspective, you could fit an entire city block, including multi-story buildings, inside a single Martian lava tube. It's a staggering thought. These aren't just caves, they are underground canyons, colossal linear caverns that could run for dozens, maybe even hundreds, of miles through the Martian subsurface. Their formation also speaks to their likely locations. We find the skylights most often on the flanks of those giant volcanoes and within the vast canyon system of Valles Marineris. And that's no coincidence. These were the areas of the most intense and prolonged volcanic and tectonic activity. The lava flows there would have been persistent and enormous, perfect conditions for creating the biggest and most stable tubes. Now, another critical question is, how have these hollow, presumably fragile structures survived for billions of years? Mars has earthquakes, or rather Marsquakes, meteorite impacts, and the relentless pull of gravity itself. The answer lies in the Martian environment and the nature of the rock. First, the lack of liquid water and significant atmospheric weathering is a huge factor. On Earth, our caves are constantly being modified by water seepage, which dissolves rock, enlarges passages, but also weakens structures. On Mars, that process is virtually non-existent. What you get is a kind of geological deep freeze. The tube forms, the lava drains, and then it just sits there, untouched. Second, the rock itself, basalt, is very strong, and in the low-gravity environment, the structural stresses are much lower. There's also no heavy rainfall to lubricate cracks, no tree roots to pry things apart, no freeze-thaw cycles of water to act as a destructive wedge. The regolith, the Martian dust and broken rock, is also very dry and likely has a certain amount of cohesion, helping to shore up slopes and openings. So, while the surface of Mars is being slowly sandblasted by dust storms, the underground world, once formed, enters a state of profound preservation. This makes these lava tubes more than just empty spaces. They are genuine time capsules. They are snapshots of the Martian subsurface from the time they formed, sealed off from the extreme surface processes that have reshaped the rest of the planet. Inside, we might find pristine geological features that have long vanished from the surface, delicate lava formations like drips and shelves, perhaps even layers of volcanic ash or evidence of how the lava interacted with the ground it flowed over. The walls are a direct record of the lava's composition, temperature, and flow history from an era when Mars was still geologically alive. Understanding this genesis is fundamental to everything else about these caves. It tells us what to expect when we finally send a probe down there. We should be looking for smooth walls with flow lines, perhaps collapsed piles of rubble from partial ceiling falls, and a tunnel shape that generally follows the downhill slope of the ancient terrain. It tells us these aren't random, chaotic caverns, but structured, predictable geological formations. This origin story also frames the central promise and challenge of these spaces. Their immense size and structural integrity are what make them so tantalizing for future human habitation. They offer ready-made, gigantic shelters, but that same genesis means they are utterly dark, completely sealed off from the sun, and were formed in an environment devoid of any life-friendly conditions at the time. Any potential for life inside them would have to come later, from other processes, like water seeping in from different sources or chemical reactions creating niches for microbes. The lava tube itself is just the empty house. Whether anything ever moved in is the next great mystery. So, as we stand at the conceptual edge of these skylights, knowing they lead into the guts of ancient lava tubes completely changes our perception. We're not looking into just a hole. We're looking into a fossilized artery of a once fiery planet, a preserved piece of infrastructure from Mars's volcanic heyday. This architectural origin is what gives these caves their grandeur, their stability, and their incredible potential. They are a direct legacy of the most powerful forces that ever shaped Mars, frozen in time and waiting, in the perfect silence of the subsurface, for a visitor from Earth to finally turn on a light and see what secrets have been hiding in the dark for billions of years. The stage was set by geology on a planetary scale, and now the next act, the act of exploration, is ours to write. This understanding of their formation is the bedrock, literally and figuratively, upon which all our plans and dreams for these subterranean worlds must be built. It tells us the how and the why of their existence, providing the essential context for every sample we might take, every measurement we might make, and every step a future explorer might take in that profound, otherworldly darkness. The sheer scale is humbling, a reminder that nature's construction projects can dwarf our greatest earthly imaginations, especially when the rules of physics are subtly different. That architectural marvel, the preserved lava tube, offers more than just a fascinating geological history. It provides something even more critical for the future of Mars exploration. Sanctuary. Dot. The moment you descend through a skylight and leave the surface behind, you enter a realm that is fundamentally different in a way that matters most for survival. The surface of Mars is a breathtaking but deadly place. And one of the biggest reasons is the constant, invisible hail of high-energy radiation. This isn't a minor concern. It's a showstopper for long-term human presence and a major limiting factor for the preservation of any potential evidence of life. To understand why these caves are such game changers, you have to first grasp the radiation problem. Earth is incredibly fortunate. We have two powerful layers of defense against the harsh radiation of space. First, our planet has a strong global magnetic field generated by its molten core. This magnetic field acts like a force field, deflecting a huge portion of charged particles from the sun and deep space, bending them away from our atmosphere. Second, we have a thick, robust atmosphere. The molecules in our air act like a physical shield, absorbing and scattering much of the radiation that does make it through the magnetic field. The result is a relatively safe environment at ground level. Mars has neither of these things. Its global magnetic field collapsed billions of years ago, leaving the planet exposed. It does have a very thin atmosphere, about 1% the density of Earth's, but it's utterly inadequate as a radiation shield. This means the Martian surface is bombarded by two main types of radiation: galactic cosmic rays and solar energetic particles. Galactic cosmic rays are exactly what they sound like: extremely high energy particles, often heavy ions, originating from outside our solar system. They travel at nearly the speed of light and can penetrate deeply into any material. Then you have solar energetic particles, which come from our sun during solar flares and coronal mass ejections. These are bursts of protons and other particles that can deliver intense, acute radiation doses for any robotic rover or potential astronaut on the surface. This is a constant, pervasive threat. Radiation doesn't just pass through you harmlessly. These high-energy particles smash into the atoms in your body, breaking molecular bonds and damaging cells. Most critically, your DNA. This damage can lead to increased cancer risk, cataracts, central nervous system effects, and sickness from acute exposure. For electronics, it can cause bit flips, memory damage, and component failure over time. For the search for life, it's equally destructive. Complex organic molecules, the kind that might serve as biosignatures or even the remains of past microbial life, get broken apart and degraded by this relentless radiation over geologic timescales. The surface soil is essentially sterilized down to at least a meter or more. So, if you're looking for pristine, preserved organic material, the surface is the last place you'd find it. This is where the simple, massive physics of a cave wall changes everything. Rock is an excellent radiation shield. The principle is straightforward. Mass stops radiation. The more material you put between yourself and the radiation source, the more particles get absorbed or deflected. The thick roof of a lava tube, which could be tens of meters of solid basalt, acts as a phenomenal natural barrier. It's like putting a mountain over your head. Studies using data from orbiters and surface rovers have modeled this effect. On the surface, the radiation dose is about 200 to 300 times higher than on Earth's surface, but just a few meters underground, that dose rate plummets. Estimates suggest that beneath about 3 meters of regolith or rock, the radiation environment could become comparable to natural background levels on Earth. Inside a large lava tube with a roof tens of meters thick, you are in one of the most radiation-protected environments possible on the entire planet. This transforms the scientific narrative completely. If you want to search for signs of life, whether past or present, you must go where the radiation hasn't spent billions of years shredding the evidence. The cave becomes the ultimate protective vault. Any organic molecules, any delicate fossil structures, any chemical biosignatures that might have been washed in, blown in, or formed in place within that cave have been sitting in a dark, cold, and crucially, radiation-shielded environment. Their chances of preservation are orders of magnitude higher than anywhere on the surface. This makes caves not just interesting targets, but the highest priority targets in the search for life on Mars. For future human explorers, the implication is even more direct. Astronauts on the surface would need to live in habitats with significant radiation shielding, which means lugging heavy materials from Earth or figuring out how to manufacture shielding locally using Martian regolith, a complex and energy-intensive process. But a pre-existing cave offers a ready-made, structurally sound foundation for a habitat that is already shielded. You could build your pressurized modules inside the cavern, and the mountain above you does the shielding work for free. This isn't just about reducing long-term cancer risk. It's about enabling missions of longer duration and making a permanent presence feasible. It also protects against other surface hazards, like micrometeorites, which the thin atmosphere does little to stop. A cave ceiling would catch any small debris. This combination of natural protections fundamentally alters the engineering and logistical equations for human settlement. The cave transitions from being a scientific curiosity to a strategic resource. It's a place where both machines and humans can operate with a significantly reduced environmental threat. This protective quality also shapes the kind of life we might look for inside. The cave's interior is impermanent, absolute darkness. That rules out photosynthesis as an energy source, but in the radiation-safe, stable dark, other forms of metabolism could potentially persist. On Earth, we find ecosystems in deep caves and around hydrothermal vents that are based on chemosynthesis, where microbes derive energy from chemical reactions between rocks and water, for instance, oxidizing minerals like iron or sulfur. A Martian cave, especially one that might have occasional seepage of water or past hydrothermal activity, could provide a similar niche. The radiation shield means any such ecosystem, likely microbial if it exists, wouldn't have to also evolve complex DNA repair mechanisms to handle surface radiation levels. It could exist in a relatively benign subterranean environment, insulated from the apocalypse happening overhead. So, when we talk about the caves as a sanctuary, we mean it in the broadest sense. They are a sanctuary for preservation, protecting delicate chemical clues from the ravages of time and space. They are a sanctuary for potential life, offering one of the few stable, less hostile environments on the planet. And they are a sanctuary for human ambition, providing a natural infrastructure that could make living on Mars not just a daring stunt, but a sustainable endeavour. This isn't a speculative fantasy. It's a direct consequence of physics. Mass blocks radiation. Mars lacks a magnetic field and a thick atmosphere. Therefore, the only way to find a naturally low radiation environment on Mars is to go underground. The lava tubes, with their vast volumes and strong ceilings, are the perfect geological gift, offering the deepest form of shelter possible. They turn a fundamental weakness of Mars as a destination into a strength. We just have to be smart enough to use what the planet itself has already built. The journey from identifying a strange dark hole in an orbital image to recognizing it as a potential safe haven for life and human explorers is one of the most compelling stories in modern planetary science. It reframes the entire subsurface from being an afterthought to being the main event. The promise of the caves isn't just about what we might find in them, but about what they enable us to do. They offer a path forward, a way to step off the deadly surface and into a place where we, and perhaps native Martian life, could actually survive. This transforms them from mere destinations into potential homes. And that changes everything about our relationship with the red planet. The radiation shield is the silent, invisible benefit that makes all other possibilities thinkable. Without it, long-term human habitation is a grueling battle against a hidden enemy. With it, we have a fighting chance. The caves offer that chance, carved out by ancient volcanoes and preserved for eons, waiting in the dark to offer shelter to the next wave of explorers, whether they are made of silicon or flesh and blood. This protective function is the bedrock upon which the practical dream of Mars exploration is increasingly being built, turning a science fiction concept into a credible, physics-driven plan for the future. That sanctuary from radiation offers another profound benefit, one that is just as critical for both machines and any potential for life: an escape from the brutal temperature swings that define the Martian surface. Stepping into a cave is like leaving a chaotic, unpredictable climate and entering a place of profound stillness, where the very rock itself acts as a massive thermal battery, smoothing out the extremes and creating a stable, if cold, environment. To appreciate this, you need to understand just how wild the temperature ride is on the surface. Mars has a very thin atmosphere, as we know, and that atmosphere is not good at retaining heat. It's like having a terribly inefficient blanket. When the sun is shining on a spot at midday near the equator, the ground can actually get quite warm, maybe even reaching a comfortable 20 degrees Celsius or so. But that's incredibly localized and temporary. As soon as the sun sets, all that heat radiates back out into space with almost nothing to hold it in. The temperature doesn't just drop, it plummets. We're talking swings of 80, 90, even over 100 degrees Celsius between day and night. In the middle of the night, temperatures can easily drop to minus 100 degrees Celsius or colder. That's not just chilly. It's an environment that actively tries to break things through constant expansion and contraction. Now, for a robot like a rover, this is a huge engineering challenge. Everything from batteries to cameras to motors has to be designed to survive and operate through that insane thermal cycle, day after day, year after year. It requires heaters, insulation, and careful power management just to keep the electronics alive through the Martian night, for any hypothetical chemical process that might lead to or sustain life. These extremes are equally hostile. Liquid water isn't stable. It would either freeze solid or boil away rapidly at the low pressure. Organic molecules get stressed by repeated freeze-thaw cycles. It's a punishing, volatile place. Now, go underground. The moment you pass below the surface layer, you enter the domain of subsurface thermal equilibrium. The key concept here is thermal inertia. The rock and regolith of Mars have mass and density. They take a long time to heat up and a long time to cool down. The daily and even seasonal cycles of sunlight and darkness on the surface simply don't have the time or power to influence the deep subsurface. The temperature a few meters down is governed by the average internal heat flow of the planet itself and the long-term average surface temperature above. It's like how a cave on Earth maintains a roughly constant temperature year-round, regardless of whether it's summer or winter outside. On Mars, this effect is even more pronounced due to the lack of liquid water or air circulation to transfer heat. So, what is the temperature inside one of these lava tubes? It's going to be cold, undoubtedly. Estimates suggest it would roughly equal the mean annual temperature of the surface at that location. For many mid-latitude areas, that's probably around minus 60 degrees Celsius. That is still incredibly cold by human standards. But here's the crucial difference. It is stable. It isn't minus 61 moment and then 20 the next. It's a constant, predictable, steady minus 60. This stability is a game changer for several reasons. First, for potential Martian life. Stability is often more important than the absolute temperature. If there are any chemosynthetic microbial ecosystems eking out an existence, they rely on consistent chemical reactions. Wild temperature swings make maintaining metabolism incredibly difficult. A stable, if cold, temperature allows for chemical processes to proceed at a predictable rate. It also means that if there is any water present in the form of brines or thin films, its state is more predictable. It might remain liquid at lower temperatures if salts are present, and it won't be subjected to constant freezing and thawing, which can disrupt cellular structures. For the search for past life, this stability aids preservation. It's another form of protection, keeping potential biosignatures in a kind of deep freeze stasis without the damaging thermal stress cycles. Second, and perhaps more immediately practical, is the impact on future human habitation and robotic exploration. Designing a system for a stable environment is infinitely easier than designing one for a wildly variable one. Think about building a house. It's much simpler to insulate and heat a house in a cold but stable climate than it is to build one that has to handle both scorching summer heat and deep winter freezes. The same applies to a Mars habitat. A module placed inside a cave would have to deal with one primary thermal condition: extreme cold. The engineering becomes focused on efficient insulation and heating. You don't need powerful and energy-hungry cooling systems for the day or massive heating boosts for the night. The temperature outside your habitat walls isn't swinging by 100 degrees every 12 hours. This drastically reduces the complexity and, most importantly, the energy requirements of your life support systems. Energy is the currency of survival on Mars. Every watt saved on thermal regulation is a watt that can be used for something else. Life support, experiments, communication, or even leisure. The cave's natural thermal stability is like a massive subsidy for your power budget. It also reduces mechanical stress on your equipment. Metal and composites expand and contract with temperature changes. Less fluctuation means less fatigue on joints, seals, and structures, leading to greater longevity and reliability. For robots tasked with exploring the cave itself, this is also a benefit. A cave-exploring rover wouldn't need the same robust and power-intensive thermal control system that a surface rover like Perseverance requires. Its batteries could last longer, its motors could operate in a more benign environment, and it could potentially operate through what would be the surface night without worrying about freezing solid. This stability extends to the geology of the cave itself. On the surface, the repeated thermal cycling contributes to the breakdown of rock over time, a process called thermal stress fracturing. Inside the cave, that process is minimal. The pristine nature of the lava tube features, the flow lines on the walls, the possible presence of delicate mineral deposits, are all better preserved because they haven't been subjected to millions of years of daily heating and cooling pulses. This gives us a clearer window into the past. So, combined with the radiation shielding, the thermal profile of a Martian cave creates what scientists call a highly decoupled environment. It is largely divorced from the violent atmospheric and temperature cycles of the surface. It exists in its own steady state. This decoupling is what makes caves such compelling astrobiological targets. They are isolated refuges. If life ever did arise on or near the surface of Mars billions of years ago when conditions were milder, these subsurface cavities could have served as a retreat, a place where life could have persisted long after the surface became uninhabitable. They are the ultimate fallout shelters for biospheres, for human explorers. This decoupled environment is the closest thing Mars offers to a safe harbour. It's not hospitable, but it is manageable. The challenges are known and constant. You are not fighting a daily battle against a shifting environment. You are adapting to a single, persistent condition. This allows for more efficient, specialized design of everything from spacesuits for cave exploration, which would focus on insulation against constant cold rather than variable conditions, to the architecture of permanent habitats. The psychological impact shouldn't be underestimated either. While living underground has its own mental challenges, the predictability of the environment can provide a sense of stability. The external conditions aren't changing wildly outside your window. They are constant. This can simplify daily routines and planning. In essence, the thermal stability of the caves turns a major engineering and survival problem into a more straightforward one. It exchanges the chaos of the surface for the constancy of the deep. This, paired with the radiation protection, constructs a very powerful argument for the subsurface as the logical place for sustained activity on Mars. It's not the most glamorous idea, living in a hole, but from a purely practical standpoint, it leverages the natural advantages of the Martian geology to solve two of the biggest environmental threats. The caves don't need to be warmed up from -100. They just need to be warmed up from -60. They don't need a radiation shield built. They come with one pre-installed. This combination of factors is why, when you listen to scientists and engineers seriously discuss the long-term future of humans on Mars, the conversation invariably turns underground. The surface is for exploration, for resource gathering, for solar power collection, but for living, for staying, for building a lasting presence. The stable, protected depths of these ancient lava tubes offer a foundation that the harsh, exposed surface simply cannot match. The temperature stability is the silent partner to the radiation shield, a less dramatic but equally vital characteristic that transforms these caverns from mere geological curiosities into potential cornerstones for our future on another world. The stable, protected environment of those caves leads us directly to the single most compelling reason to risk a mission into the abyss. The chance, however slim, of answering the profound question of whether we are alone in the universe. This is the core of it all. The search for life beyond Earth isn't just about finding little green men. It's about finding any signature, any hint that biology is not a unique miracle of our own planet. And if such a thing exists on Mars, the subterranean caves are where we are most likely to find its traces, or perhaps even its quiet, persistent presence. We are hunting for biosignatures. That's the scientific term for any substance or pattern that provides scientific evidence of past or present life. It's a broad category because life is messy and creative. It's not one single thing. On Earth, biosignatures range from the obvious, like a dinosaur bone, to the incredibly subtle, like a specific ratio of carbon isotopes in an ancient rock that can only be explained by biological processing. In the Martian caves, we have to think like detectives looking for the faintest traces of a crime that may have occurred billions of years ago, or for a quiet tenant that still resides in the dark. The first and perhaps most direct category of biosignature is molecular. We are talking about organic molecules. Now, organic in this context doesn't mean grown without pesticides. It means carbon-based. The building blocks of life as we know it, the universe is actually full of simple organic molecules. They can form through non-biological chemistry. So finding methane or a few carbon atoms isn't enough. We are looking for the complex stuff. Think amino acids, the building blocks of proteins, or lipids, which form cell membranes. Even more compelling would be seeing a pattern in these molecules, a preference for certain types over others that mirror what life on Earth does. Life tends to be picky. It uses left-handed amino acids. For example, while non-biological processes usually make an equal mix of left and right-handed versions, finding a dominance of one type in a Martian cave sample would be a seismic discovery. The second category is morphological. This means looking for shapes and structures that resemble life on Earth. The classic example are stromatolites. These are layered rock formations created by ancient microbial mats, tiny organisms that trapped sediment and over millennia built up these distinctive, often dome-shaped structures. If we see a weird, layered, textured pattern on a cave wall or on the floor that looks suspiciously like a fossilized microbial reef, that's a potential morphological biosignature. It could also be something as small and delicate as microfossils, the mineralized remains of individual cells, preserved in the fine mud of a cave floor that was once damp. The third category is chemical or isotopic. Life messes with chemistry in predictable ways. It takes in elements and, through its metabolism, changes the ratios of different isotopes. For instance, life prefers lighter carbon isotopes. So if you analyze the carbon in a mineral deposit inside a cave and find it is heavily skewed towards the lighter isotope compared to the Martian atmosphere or non-organic rocks, that's a huge red flag that life may have been involved. Similarly, looking at minerals that typically form in the presence of biological activity, like certain types of sulfides or oxides that have a biological fingerprint. The cave environment is uniquely suited to preserving all these potential signals. As we discussed, the radiation shield protects complex molecules from being broken apart. The thermal stability means no freeze-thaw cycles to pulverize delicate structures. It's a natural preservation chamber. But we must also consider what kind of life we might be looking for. The caves are in permanent, total darkness. This immediately rules out any life based on photosynthesis. No plants, no algae. If there is life, it almost certainly would be chemosynthetic. This is a life strategy we know well from Earth's own extreme environments. In the deep ocean vents, in sulfur caves, even in rocks deep underground, microbes get their energy not from the sun, but from chemical reactions. They might oxidize iron or sulfur minerals in the rock, or they might metabolize simple gases like hydrogen or methane that seep up from the planet's interior. A Martian cave, especially one that might have had past or even present seepage of liquid water, maybe as a salty brine that stays liquid at lower temperatures, could provide the perfect niche for such a community. The search, therefore, is not for a walking, crawling creature. It is for a biofilm, a slime, a barely perceptible discoloration on a rock where microbes are actively processing chemicals. Or, more likely for our first missions, it's for the fossilized remains of such a community that thrived when Mars was wetter, a last refuge that eventually went silent. This is where the exploration strategy gets incredibly nuanced. You can't just drive a rover in, scoop some dirt, and say, "Found it." The risk of contamination is too high, both forwards and backwards. We could bring Earth microbes with us, hiding on the rover, and then discover them, which would be the ultimate scientific embarrassment. Or, in the far future, we could bring back a sample that contains a dormant but viable Martian organism. So, the instruments and protocols must be exquisitely careful. We need tools that can detect these biosignatures in situ, on the spot. Imagine a robotic arm equipped with a powerful microscope that can look for cellular shapes. Imagine a tool that does chemical analysis, like a mass spectrometer, that can vaporize a tiny grain of material and read its molecular and isotopic makeup. Imagine sensors that can sniff the cave's atmosphere for anomalous gases, like whiffs of methane or other compounds that might be waste products of a hidden metabolism. The mission would have to be a mobile laboratory, capable of performing these complex analyses deep underground, with the intelligence to recognize a promising target, a different coloured patch of sediment, a mineral vein, a spot where moisture sensors perk up, and then investigate it with a suite of tools. It's a monumental technical challenge. But let's play out the scenario. A future mission lowers a sophisticated rover into a cave. It navigates the rocky floor, its lights piercing a darkness that has been absolute for billions of years. Its instruments scan the walls. It finds a patch where the chemistry is weird. It uses a drill to collect a core sample from just beneath the surface, a place protected from any modern cosmic dust. It feeds that sample into its onboard lab. The data starts coming back. Complex organic molecules, far more complex than anything from non-biological meteorites. A strange, repeating layered structure in the rock matrix under the microscope. A carbon isotope ratio that is wildly skewed from the Martian norm. Each finding alone would be astonishing but debatable. Together, they would build a case that becomes overwhelming. The message from the control room on Earth would be one of controlled, stunned euphoria. We have a strong dot, repeatable signal consistent with a biological origin. That's the language they would use. It wouldn't be, "we found aliens." It would be a careful, scientific conclusion based on evidence that points overwhelmingly to life. The implications of such a discovery, even of past life, are hard to overstate. It would mean that life is not a fluke of Earth. It would mean that the universe is likely filled with life, if it happened twice in one solar system, on neighbouring planets. Then it has probably happened 1 billion times across the galaxy. It would redefine our place in the cosmos completely. For biology, it would be a new beginning. Is it based on DNA? Is it a mirror image of our chemistry? Or is it something utterly different? A second Genesis would give us a comparative point, a way to understand what is essential to life and what is just a local variation, for the future of Mars exploration. It would trigger a planetary protection crisis of the highest order. If there is native life, even microbial, the ethical framework for human settlement changes dramatically. We would have to ask, do we have the right to colonize a living world? Could we avoid contaminating and destroying its last surviving ecosystems? The caves would shift from being potential homes to being protected wilderness areas, sacred sites of cosmic biology. This search is the high-stakes poker game of astrobiology. The caves are the table. The ante is the cost of a multi-billion-dollar mission. The potential payoff is nothing less than a new understanding of reality. This is why scientists are so passionate about going there. It's not just another geology site. It is the most promising sanctuary, the most likely vault where the secret of life beyond Earth might have been kept safe. Every other reason to go to the caves, the radiation shielding, the stable temperatures, the potential for human habitat, is important, but this one is transcendent. It is the search for a reflection, however faint, in the dark mirror of another world. It is the ultimate act of cosmic curiosity, and it all hinges on interpreting those subtle, silent clues, the biosignatures. The mission to find them will be one of the hardest things we have ever attempted. A robotic proxy sent into the deep to answer a question that has haunted humanity for all of its existence. Are we alone? The caves of Mars hold the answer, locked in the cold, dark, and perfect silence of their ancient stone, the staggering potential of that discovery. the chance to find a biosignature in the silent dark, is what drives the entire concept forward. But between that dream and reality lies a chasm of technological challenges so profound that simply landing on the Martian surface, and feat we now consider almost routine, will look like child's play. Sending a robotic mission into a Martian cave is arguably one of the most complex engineering puzzles ever conceived in planetary exploration. It is a mission of firsts, with no precedent, where every system must be rethought from the ground up for an environment that is the antithesis of the sunny, flat plains we've targeted so far. The first and most obvious hurdle is simply getting inside. You are looking at a skylight, a vertical shaft that could be tens of meters deep, with walls that are likely uneven, crumbly, and treacherous. You cannot just drive a conventional rover off the edge. That is a one-way trip to a catastrophic crash. So, how do you descend? The solutions sound like they are pulled from a spy movie or a mountaineering manual. One leading concept is a rover equipped with a rappelling system. Think of a robotic climber. The rover would anchor itself securely at the rim, perhaps using drills or inflatable bags to grip the rock, and then lower itself down on a tether, a strong cable reeled out from above. It would have to control its descent perfectly, avoiding collisions with the wall, all while managing its own power and keeping its sensors aimed at the surroundings. Another idea involves tethered platforms or even a system where a stationary lander acts as a winch, lowering the explorer down like a bucket into a well. Then there is the concept of legged or sphere-shaped robots that could be dropped or could roll down the slope, using their articulation to survive the fall and right themselves at the bottom. Each method carries immense risk. The tether could snap or snag. The anchor could fail. The robot could tumble and land upside down. A death sentence. This single act of entry is a mission-critical event with no do-overs, happening minutes or hours after commands are sent from Earth, with real-time control impossible once inside. If it survives the descent, a new set of problems emerges, starting with the most fundamental: communication. Radio waves, our lifeline for all previous rovers, cannot penetrate solid rock. The moment your robot passes below the lip of the cave, it goes completely, utterly silent to Earth. It is on its own. This necessitates a revolutionary communication architecture. The most likely solution is a communications relay system, the component that stayed at the surface, perhaps the lander or the anchor station, becomes a vital partner. It would need a powerful antenna pointed at Earth satellites or directly home. The subterranean rover would talk to this surface partner using a different method, perhaps ultra-high frequency radio if the line of sight is clear, or even a physical tether that carries fiber optic signals. Some concepts imagine the rover leaving behind a breadcrumb trail of small, wireless communication nodes as it explores, creating a network that relays signals back to the surface station. But any break in that chain, and the rover is lost. All its precious data, its discoveries, would be trapped forever in the dark. This leads directly to the third monumental challenge: power. Surface rovers use solar panels. They recharge every Martian day. Inside a cave, there is no sunlight, none. The environment is permanent. Absolute darkness. Solar power is impossible. This means the entire mission must run on stored energy. That means batteries. But batteries are heavy, and they have a limited lifespan. You would need enough battery capacity to power all the systems: mobility, computing, instruments, communication, for the entire planned mission duration, which could be weeks or months. There is no recharging. Once the batteries dip below a critical level, the robot dies. For longer-term exploration, The only alternative would be a radioisotope thermoelectric generator, like the ones used on the Curiosity and Perseverance rovers. These devices use the heat from the decay of plutonium to generate electricity. They are compact, reliable, and can last for years, but they are also complex, expensive, and raise safety and regulatory hurdles. Yet, for a cave mission, an RTG might be the only viable option to provide the persistent, sunlight-independent power needed for a meaningful exploration. Then there is the problem of navigation and mobility. The interior of a lava tube is not a smooth, curated laboratory floor. It is a chaotic, rocky landscape formed by collapse, fallen debris, and ancient lava flows. There could be giant boulders, steep slopes, sand traps, and jagged protrusions. The famous 7 minutes of terror for landing is replaced by a constant, low-grade terror of traversal. A robot designed for this cannot use the simple 6-wheel rocker bogie design of current rovers. It needs extreme mobility. Engineers are brainstorming robots with legs, like mechanical insects or dogs, that can step over obstacles, or robots with wheels on articulated arms that can climb, or even rolling spheres that can deform and shift their weight. Each of these designs is more mechanically complex, more prone to failure, and harder to control than a simple wheeled rover. Furthermore, the robot must navigate this terrain with supreme autonomy. The communication delay with Earth, already up to 20 minutes each way, becomes irrelevant if the robot is out of contact. It must see its environment, map it in 3 dimensions using LiDAR and cameras, plot a safe path, and execute it, all by itself. It needs an artificial intelligence capable of hazard detection, path planning, and even deciding when a scientific target is worth a risky approach. This level of machine independence is beyond anything we have sent to another planet. The environmental unknowns pose another layer of risk. What is the atmosphere like inside? Could there be pockets of different gases? Is the dust electrostatic and clingy, ready to coat lenses and jam mechanisms? What is the exact temperature? And will it affect our lubricants and materials differently than predicted? The first mission will be gathering this basic environmental data even as it tries to perform science. Finally, there is the overarching philosophy of such a mission: redundancy and reliability. On the surface, if a rover gets stuck, engineers have days to brainstorm a solution. They can try to maneuver it out slowly. In a cave, if the robot gets stuck or falls, that is likely the end. There is no rescue mission. Every critical system needs backups. The software must be robust enough to handle countless unexpected scenarios. The mission design must accept that some level of risk is unavoidable, and that the potential reward, those biosignatures, that groundbreaking science, justifies the very real possibility of total loss. This is why a cave mission is still on the drawing board and not on a launch manifest. It is a systems engineering problem of the highest order, requiring advances in robotics, autonomy, power, and communications, all to mature simultaneously. It is not enough to have a great climbing robot. You need the climbing robot that can also host a full science lab and communicate through rock. It is a ballet of precision where every dancer, the entry system, the rover, the communicator, the power source must perform perfectly. And the first rehearsal is on another world, 200 million miles away. Yet, for all these challenges, the work is underway. Prototypes of cave roving robots are being tested in lava tubes on Earth, in deserts and on volcanoes. Engineers are running simulations of rappelling descents. Communication specialists are testing mesh networks in underground tunnels. Each small step on Earth is a step towards solving the puzzle of Mars. the first mission will not be a grand tour of a vast cavern network. It will be a cautious, focused, probably short-duration descent into a single skylight, with the primary goals of proving the entry and communication technologies, capturing the first true images of the Martian subsurface, and maybe, if everything goes miraculously well, snapping a picture of a cave wall that looks intriguing enough to warrant the next, more capable mission. It will be a technological pathfinder, a daredevil mission whose greatest achievement might simply be proving that it can be done. The robots we send will be the unsung heroes, the steel and silicon pioneers who venture where nothing has ever gone before, into a darkness older than life on Earth, carrying the fragile light of our curiosity. They will face more peril in their first meter of descent than most rovers face in a year on the surface. But if we can overcome these challenges, if we can design a machine that can descend, survive, explore, and tell us what it finds, the door to the underground Mars will finally be pushed open, and a new era of exploration will truly begin. The technological marvel that makes it possible will be, in its own right, a testament to human ingenuity, as monumental as the discovery it seeks to enable. The daunting list of challenges makes one thing perfectly clear. Before any human ever sets foot at the rim of a Martian skylight, we will send our robotic ambassadors. These machines will be the true pioneers, bearing the full weight of our curiosity and facing the immense risks of the unknown. Their design, capabilities, and very philosophy of operation will be fundamentally different from anything we have sent to Mars before, because the job is fundamentally different. This isn't about traversing a sunlit plain. It's about conquering a vertical, dark, and isolated labyrinth. The first wave of explorers will not be the wheeled, solar-powered rovers we know and love, rovers like Spirit, Opportunity, Dot, and Perseverance are magnificent machines, but they are built for the surface. Their mobility systems are designed for rocky ground, not for descending cliffs or navigating chaotic boulder fields inside a cave. A new breed of robot is required, one with radical mobility. Engineers are looking at many fascinating concepts. One strong contender is the legged robot. Imagine a mechanical spider or a dog with 4 or 6 articulated legs. This design offers incredible flexibility. It could step over obstacles, carefully place its feet on unstable rubble, climb steep inclines, and even potentially right itself if it tips over. The trade-off is complexity. Legs have more moving parts than wheels, which means more potential points of failure. The software to control walking, balancing, and deciding where to step is immensely more complicated than the software for driving wheels. Another concept is a hybrid system, a rover with wheels, but with wheels mounted on articulated arms. This machine could drive normally on flat sections, but then use its arms to climb over large blocks or even lower itself down short drops. Then there are more exotic ideas, like robots that are essentially rolling spheres, using internal weights to shift their centre of mass and propel themselves, which could be very robust for tumbling down slopes. The key for any of these designs is not just mobility, but autonomous mobility. The communication blackout we discussed means the robot cannot wait for step-by-step instructions from Earth. It must perceive a jumble of rocks, shadows, and holes, and in real time, calculate a safe path forward. This requires a suite of advanced sensors. It will need multiple cameras for stereoscopic vision, creating a 3-dimensional map of its surroundings. It will likely use LiDAR, which works like radar, but with laser light. to precisely map the distance to every object around it, even in total darkness. These sensors feed data into an onboard computer running sophisticated algorithms for something called SLAM, simultaneous localization and mapping. In essence, the robot is building a map of its environment while simultaneously figuring out where it is on that map, all without GPS or any pre-existing charts. This technology exists on Earth for self-driving cars and some drones, but making it robust enough to work on another planet, with no human intervention, is a huge leap. But the first entity through the skylight might not be a rover at all. It might be a drone. We have proven the concept of powered flight on Mars with the Ingenuity helicopter, a breathtaking success that opened everyone's eyes. For cave exploration, a small, autonomous drone could be the perfect scout. Imagine it being lowered into the skylight on a tether, then released. It would activate its rotors and fly into the cavern. Its mission would be rapid reconnaissance. In a matter of minutes, it could map the immediate area around the entrance, identify major obstacles, spot potential pathways for a rover, and even give us our first breathtaking panoramic views of the Martian underground. It could use its own LiDAR and cameras to create a detailed three-dimensional model of the cave's geometry. This information would be priceless for planning the rover's first moves. The drone might then return to its docking station on the surface lander to recharge and transmit its data. Of course, cave flight presents new hurdles. The atmosphere inside might be different, denser or thinner, affecting rotor performance. There could be unexpected air currents. And the darkness is absolute, so the drone would need its own lighting and sensors to avoid flying into a wall. But the potential payoff in situational awareness is enormous, whether it arrives on legs, wheels, or rotors. The robotic pioneer will be packed with scientific instruments, but these too will be tailored for the subsurface mission. It will need powerful lights and high-resolution cameras to take the first true color images of Martian geology untouched by surface weathering. It will carry a compact spectrometer to determine the mineral composition of cave walls from a distance, looking for signs of water-altered minerals or interesting chemical deposits. A drill or abrasion tool will be essential to get below the dust-covered surface of rocks to sample pristine material. Most importantly, it will need instruments capable of detecting biosignatures. This could include a microscope to look for microscopic structures, a laser spectrometer to analyze the molecular and isotopic makeup of samples, and sensors to sniff the cave atmosphere for trace gases like methane. Given the communication delay and blackout, the robot's brain must also be a scientist. It needs a level of machine intelligence we call science autonomy. This means it can look at its sensor data, recognize something interesting, say dot, the unusual white crust on a rock or a crack that seems to be emitting a different gas, and make a decision on its own to go investigate. It might decide that a particular rock is worth the risk of a difficult climb, or that a soil sample from a certain spot has higher priority. This turns the robot from a remote-controlled puppet into a true field partner, an extension of the science team's will that can make real-time decisions 200 million miles away. All of this advanced capability demands power, and as discussed, that means either massive batteries or a small nuclear power source like an RTG. The weight and heat management of an RTG would influence the entire robot's design. Its mission duration could then be years, not days, allowing it to venture deep into the cave network. The relationship between these robotic pioneers will likely be a team effort. A surface lander handles communication with Earth and provides power and a base. A drone conducts the initial scouting flight. Then a highly autonomous rover descends to do the detailed exploration, possibly communicating with the lander via a tether or a wireless node dropped by the drone. This multi-agent system spreads out the risk and the capabilities. They are the eyes, hands, and feet of humanity in that alien darkness. Their success would pave every inch of the way for what comes next. Every rock they catalogue, every gas measurement they take, every image they beam back builds the foundational knowledge necessary for the next, more complex mission. They will find the answers to basic but critical questions. Is the floor stable? Is the air static, or does it move? How far does the cave go? Are there side passages? Is there ice? Their very tracks? Or footfalls? In the dust will be a historic moment, the first disturbance in an environment that has been still for maybe 1 billion years. These robots represent the cutting edge of our technology, a fusion of robotics, artificial intelligence, planetary science, and sheer engineering courage. They will be built with redundancy, with multiple ways to overcome obstacles, because the price of failure is the loss of all that potential knowledge. Sending them is a statement of intent. It says we are serious about exploring the full planet, not just its easy-to-reach surface. It acknowledges the risks, but declares that the quest for knowledge, for that possible biosignature, for that understanding of Martian history, is worth the price of admission. When that first robotic pioneer switches on its lights in the eternal dark, it will be a moment akin to the first footsteps on the moon, but inverted. Instead of stepping out into a bright, new expanse, we will be peering into a hidden, ancient depth. The data it sends back will not just be science. It will be the first pages of a whole new chapter in the story of Mars, written by our silent, mechanical proxies. They go first so that we, one distant day, might know if it is safe and worthwhile to follow. Their journey into the abyss is the necessary, courageous prologue to our own. It's a long shot, but conceivable. Analysing the isotopic ratios of gases in a cave, comparing the proportion of different types of argon or xenon atoms to those on the surface, could tell us if the cave air is indeed a relic, a time capsule of an ancient Martian climate. This would be like opening a geology textbook and finding a preserved sample of Earth's air from the age of the dinosaurs. But for another world entirely. The robotic explorer tasked with measuring this will need a sophisticated atmospheric suite. It would have a tiny weather station, pressure sensors, temperature sensors, and humidity detectors. But more importantly, it would have a mass spectrometer or a tunable laser spectrometer, instruments capable of identifying specific gas molecules and their isotopic fingerprints with incredible sensitivity. The robot might periodically take a gulp of the cave air, analyze it, and store the data to transmit when communication is re-established with the surface relay. It could also monitor for changes over time. Is the pressure constant? Does the methane concentration spike at certain times of the Martian year or after a local Marsquake? These dynamic changes would be the most exciting data of all, pointing to an active, breathing subsurface system. The implications of a unique cave atmosphere are vast for astrobiology. A slightly denser, chemically richer atmosphere could create more favourable microenvironments for any extant life. It could also enhance the preservation of organic materials by providing a buffer against oxidation. For the geology, the atmospheric composition is a direct clue to subsurface processes. Certain gas mixtures are telltale signs of specific water-rock interactions, like serpentinization, a process that on Earth supports entire ecosystems in the deep ocean crust. Finding that gas blend in a Martian cave would be a strong indicator that such life-supporting chemistry has occurred, or is still occurring, below our feet. For human exploration, Understanding the cave air is a matter of safety and utility. First, is it breathable? Absolutely not. It would still be overwhelmingly carbon dioxide and far too thin. But knowing the exact composition and pressure is critical for designing life support systems and for assessing any potential resources. Could we extract and concentrate useful gases? For example, DOT. If the cave air has a higher water vapor content, it might be more efficient to extract drinking water from the atmosphere there than from ice mining. Nitrogen DOT, crucial for a breathable air mix for habitats, is a trace gas on the surface. A cave with a slightly enriched nitrogen pocket would be a valuable find. The atmospheric data also tells us about ventilation. Is the cave a dead end, with perfectly still air? Or are there cracks and connections that allow for very slow exchange with the surface or other caverns? This has implications for contamination. A sealed, still cave might be more pristine, but also might accumulate any gases we introduce from our machinery. A ventilated cave might be cleaner for human occupation, but could also mean any native biosignatures are more diffuse. The first measurements will be transformative. Simply confirming that the cave air is identical to the surface would be a valuable, if less exciting, result. It would suggest the space is well ventilated and dynamically connected. But if the robots beam back data showing anomalous readings, a spike of methane at 10 parts per billion, a pressure reading a few percent above the local surface norm, a whiff of hydrogen sulfide, the entire scientific community would shift into high gear. That cave would become the #1 priority for follow-up missions. It would be the place where the hidden Mars is whispering its secrets through its air. Ultimately, the atmosphere inside a Martian cave is more than just a medium to move through. It is a fluid record. It is an archive of gases that can tell stories of volcanic outgassing, of ancient climate collapse, of ongoing chemical dialogues between rock and void, and perhaps, just perhaps, of the gentle exhalations of a living system too small to see. When our robotic proxy takes its first atmospheric sample in that eternal dark, it will be tasting a vintage that has matured in complete isolation for eras beyond human comprehension. Each molecule in that sample is a messenger, and we are finally building the instruments to listen to what they have to say. This investigation turns the cave from a static geological formation into a potentially dynamic chemical environment. It adds a fourth dimension, time, to our exploration. We are not just looking at frozen lava flows, we are sensing the slow, subtle processes that may still be shaping this hidden world. The air, or lack thereof, is a fundamental part of the cave's character, and understanding it is a prerequisite for understanding everything else we might find there. It is the invisible context for all the visible wonders, and unlocking its composition is the key to discerning whether the cave is a sterile tomb, a chemical reactor, or something infinitely more profound. The robotic explorers are our senses in that environment, and their atmospheric sensors are perhaps their most delicate and revealing organs, capable of smelling the history and potential of Mars in a way our own noses never could. This line of inquiry exemplifies the depth of true planetary science. It's not just about the grand vistas, but about the subtle chemistry, the whispers in the gas, the faint traces that reveal a world's hidden nature. As we prepare to send our mechanical ambassadors downward, equipping them to read this gaseous manuscript is as important as giving them eyes to see or drills to touch. The story of the Martian caves is written in the walls, the floor, and crucially, in the silent, still air that fills the space between. That atmospheric investigation, the search for trace gases and whispers of vapour, leads us directly to the most tangible and potentially transformative resource these caves might offer: water itself, locked away as ice. the tantalizing possibility of substantial, accessible water ice in the Martian subsurface isn't just a scientific hope, it's a practical necessity for the future. And caves are one of the best places we can imagine to find it preserved. We know water once flowed on Mars. The evidence is carved into the landscape in the form of dry river valleys, gigantic flood channels, and sedimentary deposits. We also know a lot of that water didn't just vanish into space. A significant fraction of it likely retreated underground, where it could be stable as ice, protected from the harsh surface conditions. Orbital data from instruments like ground-penetrating radar strongly suggest vast reservoirs of water ice in the mid-latitudes, just beneath a thin layer of dry regolith. But on the surface, exposed water ice sublimates. It turns directly from solid to gas in the low pressure, unless it's buried. This is where caves change the equation. A cave is a natural deep freeze and a natural shield. Its interior is permanently cold, hovering around that stable minus 60 degrees Celsius we talked about. More importantly, it is protected from the direct reach of the sun and the atmospheric conditions that drive sublimation on the surface. Think of it like a walk-in freezer versus leaving an ice cube on the sidewalk. The cave is the freezer. Inside, water ice could persist for billions of years with minimal loss. So, what would this ice actually look like? It probably wouldn't be a shimmering, smooth skating rink. The reality would be more varied and possibly even more interesting. One possibility is hoarfrost, or ice films coating the walls. In the constant cold, any tiny amount of water vapour in the cave atmosphere could condense and freeze directly onto the rock surfaces, creating delicate, crystalline patterns. Another possibility is layered deposits on the cave floor. Imagine dust and ice laid down in alternating layers over millennia, perhaps from atmospheric dust settling and then being cemented by frost, creating a kind of icy sedimentary record. There could be pools of solid ice, perhaps covered by a layer of dust for protection, forming a frozen lake on the cave floor, or in the coldest, deepest recesses, there might even be massive ice formations, akin to glaciers, slowly flowing under their own weight over geologic time. The discovery of any of these forms would be a monumental moment. From a pure science perspective, cave ice is a treasure trove. It's not just water, it's a climate record. Each layer could trap atmospheric dust and gases from the time it formed, offering a vertical timeline of Martian climate history, much like ice cores drilled in Antarctica do for Earth. Analysing the isotopes in the water molecules could tell us about the source of the water and the temperature conditions when it condensed. It could even trap and preserve ancient atmospheric samples in tiny bubbles, giving us that direct read on Mars's past air that we speculated about. And then, of course, there is the astrobiological angle, where there is water, especially stable, long-term water. The potential for life, as we know it, increases exponentially. This ice might not be sterile. It could contain cryopreserved microbes, locked in a frozen state for eons. Or, more subtly, the boundary between the ice and the rock, where liquid water might exist in tiny, salty films, could be a habitable niche for chemosynthetic organisms. Sampling this ice carefully, melting it and analysing its chemistry and any potential biological content would be a primary goal for any cave mission. But the implications for human exploration are even more immediate and practical. Water is the key resource for a sustainable presence on Mars. It's not just for drinking. Through electrolysis, you can split water into hydrogen and oxygen. Oxygen is, obviously, for breathing. Hydrogen, combined with carbon from the Martian atmosphere, can make methane rocket fuel. So, From one resource, water ice, you can provide life support and the means to return to Earth or travel elsewhere on Mars. Finding a large dot, accessible deposit of relatively pure ice inside a cave would be like striking oil on the frontier. It would enable everything. A human base could be established near or even inside that cave, using the ice deposit as its logistical foundation. This concept, called in situ resource utilization, goes from a challenging theory to a viable plan. The cave itself provides the radiation and thermal protection. The ice provides the water, air, and fuel. It's a powerful dot, synergistic combination that makes a permanent settlement conceivable rather than fantastical. However, finding and confirming this ice is a challenge in itself. Our orbital radar can hint at subsurface ice, but it can't resolve the detailed interior of a cave from hundreds of kilometers up. The robots we send down will need tools to detect it. They might use radar again, but miniaturized, to scan the cave floor and walls for reflections that indicate ice layers. They could use neutron spectrometers, which detect the hydrogen signature in water molecules. They might use thermal sensors to look for anomalies. Ice will have a slightly different temperature signature than dry rock, and ultimately, they would need a drill. A robotic drill that could core into the cave floor, extract a sample, and then deliver it to an onboard oven or melter for analysis would be the definitive proof. The technical hurdles are significant. Drilling in a low-gravity, low-temperature environment, with a robot operating autonomously, is no small feat, but the potential reward justifies the effort. The very act of discovering ice would reshape mission architectures for decades to come. Let's imagine a scenario. A robotic mission descends into a promising skylight. Its ground-penetrating radar shows a strong, reflective layer about 1 meter beneath the cave floor sediment. The rover navigates to that spot, uses a small drill to penetrate the surface, and retrieves a core. The core is brought into a sample chamber, heated, and the vapors are analysed. The spectrometer spikes with the unmistakable signal of water. Data transmitted to the surface relay and then to Earth confirms. Water ice, dot, in abundance, in a Martian cave. That single data point would trigger a cascade of new plans. Follow-up missions would be designed explicitly for ice resource prospecting. They would map the extent of the deposit, assess its purity, and test prototype equipment for mining and processing it. The site would be evaluated not just as a science station, but as a potential homestead. The psychological impact on the public and on the space agencies would be profound. Mars would transform from a distant, arid curiosity to a world with a tangible, usable resource necessary for sustained exploration. It makes the dream concrete. Of course, we must temper expectations. The ice might not be there in every cave. It might be deeply buried, or mixed heavily with rock and dust, making extraction difficult. It might contain perchlorates or other toxic salts common on Mars, requiring additional processing to make it safe. But the search is imperative because the payoff is so high. It represents a convergence of scientific wonder and practical survival. The caves offer the perfect storage conditions, and our exploration is the key to the lock. In the end, the quest for subsurface ice in Martian caves is a quest for independence. It's about moving from taking everything with us to living off the land. It's about turning Mars from a destination into a home. That ancient water, frozen in the dark, is the potential lifeblood of a future Martian civilization. It connects the planet's wet past to humanity's possible future. The robotic pioneers we send won't just be looking for fossils. They'll be looking for the foundation stones of our own extended presence in the solar system. They will be prospectors in the truest sense. And their discovery could be the one that changes everything, proving that Mars isn't just a place to visit, but a place where we could truly stay, fueled and sustained by the resources it hid away in its most secret, sheltered places. The journey to find that ice is a critical path in the larger journey to make humanity a multi-planet species. What if the floor sediments are easily compacted for building foundations? The geology informs the engineering. In essence, the cave is a museum and a laboratory combined. Each feature is an exhibit, waiting to be interpreted. The first robotic geologist to enter will have the unparalleled privilege of conducting the first true field geology of the Martian subsurface. Its cameras will capture vistas no human or machine has ever seen. The intricate texture of a lava flow that stopped and hardened in an instant, billions of years ago. The glitter of a mineral vein formed in a long-lost trickle of water. The gentle slope of a dust dune that settled in perfect stillness. This isn't just about collecting rocks. It's about reading a story. The story of fire, as lava carved the tube. The story of water, perhaps, as it later seeped in and deposited minerals. The story of air, as dust settled grain by grain. And maybe, just maybe, the story of life, if it ever added its own brief footnote to the narrative. The deep geology of the Martian caves is the foundational text. Before we can understand the resources, the habitability, or the potential biology, we must understand the stage upon which all those dramas might have played out. The walls hold that truth, in their composition, their shape, and their very stillness. Our exploration will translate that stone language into a history we can understand, completing a chapter of Mars's story that has been hidden in the dark, waiting for a reader with a flashlight and a curious mind. This makes the geological mission arguably the most fundamental of all the cave's scientific pursuits, the baseline from which every other question derives its context and meaning. That deep geological record, the pristine story written in the rock, isn't just a history lesson. It is the very blueprint for a potential future. Once we understand the structure and composition of these caves, their true transformative potential for human exploration comes into sharp focus. The conversation shifts from "can we visit Mars" to "can we live there?" And the caves offer a compelling answer that surface-based approaches struggle to match. For long-duration human missions, let alone permanent settlement, the problems are stark. Radiation, temperature extremes, micrometeorite risk, and the colossal expense and difficulty of shipping or building everything from scratch. The cave environment directly mitigates the most critical of these challenges in a way that feels almost providential. The first and most significant advantage is the natural protection we've already discussed, but its importance for humans cannot be overstated. On the surface, astronauts would need habitats with extensive shielding. This usually means either building structures with walls several meters thick of regolith, a massive, dirty, and risky excavation and construction project, or incorporating complex water or polyethylene shielding into the habitat walls, adding enormous weight. A lava tube provides that shielding for free. The tens of meters of rock overhead reduce galactic cosmic ray and solar particle radiation to near-Earth background levels. This isn't just an improvement. It's a fundamental change in the safety paradigm. It means astronauts could live and work without constant, career-limiting radiation exposure, and their habitat wouldn't need to be a fortress just to keep them safe from invisible particles. Similarly, the cave ceiling is a perfect bumper against micrometeorites. The thin Martian atmosphere does little to burn up small debris, so surface structures are vulnerable to sandblasting and potential punctures over time. Underground, That threat is virtually eliminated. The second pillar is thermal stability. We've talked about the wild temperature swings on the surface. A habitat there is like a house in the most extreme desert imaginable, battling blistering daytime heat and deep nighttime cold. The energy required to maintain a shirt-sleeve environment inside is enormous, taxing life support systems and power generation. In a cave, the environment is a constant, deep chill. But it is a known and stable chill. Heating a space from a constant -60 degrees Celsius is actually a simpler, more efficient engineering problem than cooling it from +20 and then heating it from -100 every single day. The habitat's thermal regulation systems can be optimized for one primary task: adding heat. This drastically reduces the complexity and energy budget, which is everything when you're generating power from limited solar arrays or a small nuclear reactor on the surface above. The third advantage is the sheer volume of pre-existing, architecturally sound space. We're not talking about squeezing a few inflatable modules into a tight hole. The potential scale of these lava tubes means they could accommodate vast, open volumes. Imagine deploying a series of modular habitats, laboratories, and communal spaces inside a cavern the size of a cathedral. There's room for growth, for separation of functions, for storage, even for large-scale agriculture under artificial light. This isn't just living in a can. It's establishing a vertical village within a protected, enclosed environment. The rock walls provide excellent anchor points for securing structures and running utilities. You could even imagine sealing off sections of the cave with bulkheads to create multiple redundant pressurized volumes. A key safety feature. The fourth, and perhaps most practical, advantage ties directly to the potential discovery of resources like water ice. A cave that contains accessible ice deposits transitions from a good site to a perfect one. It creates a closed-loop system. The cave provides shelter. The ice provides water, air, and fuel. This is the holy grail of in-situ resource utilization. A base positioned near such a deposit could achieve a high degree of self-sufficiency. Water for drinking, hygiene, and growing plants. Oxygen for breathing, hydrogen and oxygen for fuel to power rovers, or, crucially, for ascent vehicles to return to orbit. The logistics chain from Earth, which is astronomically expensive and risky, becomes simpler. You're not shipping every drop of water. You're shipping the machines to extract and process it. This changes the entire economic and practical model for sustained presence. There's also a psychological aspect often overlooked. The surface of Mars is breathtaking but profoundly hostile and lonely. An endless, barren landscape under a pink sky, with no visible life, can be psychologically taxing. A cave, while enclosed, offers a different kind of environment. It can be perceived as a womb, a safe haven. The vast interior space, once illuminated, could be configured to feel more like a structured, human-scale settlement, with controlled lighting, perhaps even simulated daylight cycles on the ceiling, and the ability to create gardens and open communal areas. The cave could foster a greater sense of security and community than a small cluster of surface modules exposed to the relentless elements. It's a place to come in from the cold, literally and metaphorically. Of course, this doesn't mean building a cave base is easy. The challenges are immense. Access is the first huge hurdle. Getting people and massive amounts of equipment safely down a vertical skylight will require technology we haven't built yet. Elevators, cranes, or pressurized tunnels drilled from the surface. The interior, while spacious, will need extensive preparation, leveling floors, securing loose rock, installing pervasive lighting, life support, and power systems. The cave atmosphere, while stable, is not breathable and will need to be managed. Any dust disturbed will be a perpetual issue for machinery and human lungs. There are also potential geological risks like minor Marsquakes or the very slow, gravitational creep of the cave structure over centuries, but these are largely engineering problems with conceivable solutions. The surface, by contrast, presents fundamental environmental problems, radiation and extreme temperature swings that require constant, energy-intensive countermeasures. The cave offers a natural solution to the hardest problems, allowing engineers to focus on the solvable ones of access and infrastructure. In the long-term vision, these subsurface settlements could become the first true cities on Mars. Networks of caves could be connected by tunnels or surface transportation. Different caves could specialize, one for primary habitation, another for intensive agriculture under full-spectrum lights, another for industrial fuel production from ice mining. The concept scales in a way that surface domes, which require building every square metre of protected volume from scratch, do not. Therefore, the impact of caves on human exploration is foundational. They reframe the goal from surviving a short expedition to establishing a permanent foothold. They turn Mars from a camping trip into a homesteading opportunity. By leveraging the natural architecture of the planet itself, we dramatically lower the barriers to a sustained, growing, and eventually self-sustaining human presence. The robotic missions we send first are the scouts for this future. They aren't just looking for science. They are conducting real estate assessment. They are checking the foundation, testing the walls, and prospecting for the water that will make the whole endeavour possible. When we finally see a robot's light illuminate the vast, empty vault of a pristine lava tube, we are not just looking at a geological wonder, we are looking at a potential home. That shift in perspective is everything. It moves the human future on Mars out of the realm of speculation and into the realm of practical planning, with the caves providing the natural infrastructure upon which our dreams can be securely built. The journey to understand these spaces is, ultimately, the first step in learning how to live within them, turning the most sheltered places on Mars into the cornerstones of humanity's interplanetary future. That vision of a safe, spacious underground home is incredibly compelling, but it exists on the other side of a gauntlet of very real and largely unknown dangers. The promise of the caves is matched, perhaps even exceeded, by the myriad risks that come with exploring a sealed, ancient, and alien subterranean environment, venturing into these spaces, whether with robots or eventually with humans, is not a stroll into a prepared tunnel. It is an expedition into a realm where a single misstep or unforeseen event could end the mission, or a life. The first category of risk is geological. We talk about these lava tubes being stable, and on geologic timescales, they are. But on the timescale of a mission, they are untested. The structures are billions of years old. While the lack of water erosion and seismic activity on Mars compared to Earth is a point in their favour, the planet does experience Marsquakes. Even a minor tremor, undetectable on the surface, could trigger a rockfall inside a cave. The ceiling and walls, while seemingly solid, could harbour cracks and weaknesses, the act of a heavy rover moving across the floor, or the vibrations from drilling, could disturb a delicate equilibrium and cause a localised collapse. Loose rubble slopes, akin to scree slopes on Earth mountains, could give way under weight. Assessing this stability from a distance is nearly impossible. The first robot inside will be both explorer and structural tester. Its every movement or experiment in the integrity of the ground beneath it. Then there is the dust. Martian regolith is not like Earth dirt. It is incredibly fine, abrasive, and almost like powdered glass due to its volcanic origin and lack of weathering. On the surface, it's a nuisance that coats solar panels and gets into mechanisms. Inside a confined cave, it could become a critical hazard, disturbing the floor. Whether by driving or digging, will kick up clouds of this dust. It will cling to everything due to static electricity. It could clog filters, jam moving parts, abrade camera lenses, and coat thermal radiators, causing equipment to overheat. For a human mission, the dust becomes a toxic and invasive threat. It could damage spacesuit seals, be tracked into habitats, and if inhaled, could cause serious lung damage akin to silicosis. The behaviour of this dust in a closed, low-gravity, low-pressure environment is something we can only poorly simulate on Earth. Next comes the biological risk, which operates in two directions. First, forward contamination, the risk that we send Earth microbes to Mars on our robots, and they survive, proliferate in a cave environment, and contaminate the very samples we seek to study. This would not only ruin the science, but could constitute an unethical invasion of a pristine alien environment. Ensuring our robots are sterilized to the highest standards is paramount, but the descent into a cave adds new contamination vectors, like dust kicked up from the sterilized rover mixing with potentially native cave dust. Second, and more dramatic, is back contamination. The risk that we bring something back, if there is extant Martian life in those caves, even microbial. It is an unknown. Could it be pathogenic to humans or Earth's biosphere? The probability is considered extremely low, as any Martian life would have evolved along a completely separate path. But the consequence could be catastrophic. This risk drives the concept of planetary protection, which would demand any samples returned from a cave, especially ones with potential biosignatures, be treated with maximum containment, possibly even studied in a remote orbiting lab before being brought to Earth. The absolute darkness and complex layout present a profound operational risk. There is no ambient light, none. If the primary lighting systems fail, the mission is blind. Navigation becomes a nightmare of relying on potentially fallible inertial sensors and preloaded maps. The cave could be a labyrinth, with side tunnels, multiple levels, and dead ends. A robot could become irretrievably lost mere hundreds of meters from the entrance. Communication, as discussed, is fragile. The loss of the relay link strands the robot, a silent tomb of data. For humans, these factors are magnified. A suit lamp failure could be fatal. A wrong turn in a maze of identical-looking lava tubes could lead to a desperate search and rescue scenario with no hope of external help for months. The environment itself holds physiological risks for future crews. The constant, unchanging darkness could disrupt circadian rhythms, leading to sleep disorders and depression. The confinement, while in a large space, is still a form of isolation. The knowledge that you are buried under millions of tons of rock, with no quick way to the surface, could induce claustrophobia or anxiety, even in trained astronauts. Then there are the pure unknowns, the unknown unknowns. Could there be pockets of different toxic gases trapped in subchambers? Is the rock electrically conductive in a way that could cause problematic static discharges? Could there be unusual chemical or even electrochemical processes on the rock surfaces that degrade materials or pose a health hazard? The first missions will be discovering these parameters in real time. Every step is a step into the untested. The price of discovery, therefore, is not just money and engineering effort. It is the acceptance of significant risk. This dictates a philosophy of extreme caution and redundancy. Robotic missions will need multiple, independent communication pathways. They will need robust self-righting mechanisms. Their software must include sophisticated fault detection and recovery protocols to survive periods of lost communication or subsystem failures. For human missions, the requirements are even more stringent. Multiple redundant egress paths would need to be established. Habitats would require backup power and life support independent of the main systems. Extensive robotic precursor missions would be mandatory to map, assay, and literally stress test the environment before humans ever set foot inside. This isn't about being risk-averse, it's about being risk-aware. The caves offer tremendous benefits, but they demand a level of respect for the environment that we have not had to accord to the Martian surface. The surface is open, visible, and relatively understandable. The subsurface is a closed book, and we must be prepared for every page to contain a surprise. This balancing act between the incredible promise of shelter and resources and the severe, multifaceted dangers defines the entire enterprise. It means our first cave rover won't be a nimble, daring adventurer. It will be a slow, over-engineered, cautious probe, designed to survive rather than to sprint, because its primary mission is to reduce uncertainty for everything that follows. Each risk it identifies and quantifies makes the path safer for the next machine, and eventually, for people. The journey into the caves of Mars, therefore, is a masterclass in calculated risk. We go because the potential rewards are civilization shifting, scientific discovery, a foothold for humanity, resources for expansion. But we must go with our eyes wide open to the darkness, acknowledging that the very factors that make the caves so appealing, their isolation, their preservation, their separation from the harsh surface, also make them a uniquely challenging and hazardous frontier. The dream of underground cities is built on the foundation of surviving the initial exploration, and that will be a story not just of engineering brilliance, but of surviving everything a mysterious, ancient, and silent world can throw at us. The caves do not invite us, they await us, and they will test our technology and our nerve to the absolute limit. This is the sobering counterpoint to the hopeful vision, the necessary reminder that the Red Planet gives nothing away for free, and its deepest secrets will be the most costly and dangerous to uncover. Yet, it is precisely this balance of high risk against high reward that has always driven exploration, and the Martian caves represent the newest, and perhaps ultimate, expression of that eternal human challenge, that balance of risk and reward, that drive to push into the dangerous unknown, ultimately transcends engineering and science. It touches on something deeper within us, a re-examination of who we are and where we belong in the grand scheme of things, the exploration of the Martian caves, and what we might find or build there carries implications that will ripple through our philosophy, our culture, and our very self-conception in ways that are as profound as any scientific data set. Let's start with the most earth-shattering possibility, the discovery of life. It doesn't have to be a little green man, a fossilized microbe, a dormant spore, or even just the unambiguous chemical fingerprints of a past biological process would be enough. That single discovery would instantly answer one of humanity's oldest questions. Are we alone? The answer would be a resounding no. The universe would shift from a vast, empty house to a neighborhood with at least one other tenant. The philosophical impact is hard to overstate. It would suggest that life is not a miraculous, one-off fluke on Earth, but a natural, almost inevitable outcome of cosmic chemistry under the right conditions. If it happened twice in one solar system, it has likely happened 1,000,000 times across the galaxy. This changes our narrative from one of solitude to one of potential cosmic community. We would have to stop thinking of life on Earth as life and start thinking of it as Earth life. One specific example of a universal phenomenon: our theology, our philosophies of existence, our art and literature all would gradually absorb this new reality. We would have a sibling, however distant and different, and that forever alters a fundamental human perspective. But even without finding life, the act of establishing a human presence in these caves triggers a powerful cultural and historical resonance. Think about it. Our earliest human ancestors on Earth lived in caves for shelter and safety. It was our first home. Now, on another world, facing an environment even more hostile than prehistoric Earth, our technological descendants might return to the cave, not out of primitive necessity, but as a sophisticated choice for survival. There's a profound circularity there. We would be using our most advanced tools to enable a lifestyle that echoes our deepest past. This creates a potent narrative. The cave, the ancient symbol of shelter and the womb of early human culture, becomes the womb for a new, offshoot human civilization. This isn't just a practical solution. It's a story that people can connect with on a mythic level. It ties our future to our origins in a very tangible way. The culture that would develop in such a subsurface settlement would be unique, shaped intensely by its environment. Life would be entirely indoors, but in a space of potentially colossal scale. The outside would not be a landscape, but a tunnel network. The day-night cycle would be artificially imposed by lighting. This could lead to new social structures and cultural norms. The community would be necessarily tight-knit, interdependent in a way that surpasses even isolated Antarctic research stations. Their relationship with nature would be completely different. On Earth, even in a city, you see the sky, weather, plants, and animals. In a Martian cave, the entire environment is human-made or human-regulated. The only natural elements would be the rock walls, the dust, and any ice or water they mine. This could foster a culture of extreme efficiency and recycling, where every gram of water and every watt of energy is valued. It might also create a deep longing for open spaces and natural light, possibly expressed through immense digital displays simulating Earth-like vistas or through a focus on virtual reality experiences. Conversely, they might develop a distinct cave aesthetic, an appreciation for the grandeur of the natural caverns themselves, lighting them artistically and treating them as a combination of cathedral, park, and historical site. Questions of law, sovereignty, and ethics would arise with new urgency. If Mars has native life, especially in the caves we want to inhabit, we face an ethical dilemma of unprecedented scale. Do we have the right to colonize a living world? Would settling in a cave constitute an act of cosmic vandalism, destroying the last refuge of Martian biology? This would force us to define concepts like planetary protection and environmental ethics for an entirely non-Earth ecosystem. Even if no life is found, the caves are pristine geological records. Should they be preserved as wilderness areas, or are they fair game for industrial development? The decisions made would set precedents for how humanity treats other worlds, establishing a space-based ethic that could guide us for centuries. For the settlers themselves, their identity would be a fascinating blend. They would be Martians, but their home would be a specific, hidden part of Mars. They might develop a strong local pride in their cave system, its unique features, and its history of exploration. Their language would likely incorporate new words for cave features, geological processes, and social roles that don't exist on Earth. Their art and music would be influenced by their surroundings, the echoes in vast chambers, the constant hum of life support machinery, the absence of natural weather sounds. They would be the first humans for whom the planet Earth is not the world, but a bright blue star in the sky, a place of origin, but not home. This shift in perspective, from Earth-centred to multiplanetary, is perhaps the biggest cultural implication of all. It would mean humanity is no longer a single world species. Our frame of reference expands. Problems and achievements would be measured on a solar system scale. A disaster on Earth would still be a tragedy, but the survival of the species would no longer be tied to one planet. This could instill a new sense of resilience and destiny. It could also create tensions between Earth and Mars, as colonies seek self-determination and control over their resources, replaying historical patterns of colonization but in a completely new context. The journey to the caves, therefore, is more than a series of engineering problems to solve. It is a catalyst for a broad human evolution. It forces us to confront our place in the cosmos, not just in a theoretical way, but through practical action. Are we mere inhabitants of Earth? Or are we a species with the capacity and right to spread life and consciousness? The caves of Mars present a test case for this question. By choosing to explore them, we are voting for an expansive, adventurous future. By choosing to settle them, we are committing to becoming something new. The philosophical and cultural ripples of that choice will wash back to Earth, challenging our parochial views and inspiring new generations to look upward and inward simultaneously. It will reaffirm that exploration is not a luxury. It is a defining human trait that shapes our culture, our philosophy, and our destiny. The silent, dark caves of Mars, waiting in the void, are not just geological formations. They are mirrors. As we prepare to shine our first lights into them, we are also illuminating new aspects of ourselves, our courage, our curiosity, our capacity for adaptation, and our eternal desire to find our place in the story of the universe. This reflective process is an inevitable and crucial part of the journey, ensuring that as we reach for the stars, we also deepen our understanding of what it means to be human in a cosmos that is suddenly, and forever, a little less empty and a lot more inviting. The cultural narrative shifts from going to Mars to becoming Martians. And that subtle change in language represents a quantum leap in our collective imagination. It suggests a future where humanity is not defined by a single planet, but by its ability to thrive in many worlds, starting with the sheltered, secret spaces of our nearest planetary neighbour. This vision, born in the practical considerations of radiation shielding and water ice, flowers into a new chapter for our species, one written not just in rock and ice, but in the evolving ideas and cultures of the people who will one day call those dark spaces home. That profound shift in perspective, from earthbound to interplanetary, provides the enduring motivation, but it's the concrete, step-by-step roadmap that will turn vision into reality. The journey into the caves of Mars won't happen with a single, giant leap. It will be a careful, incremental staircase of missions, each building on the lessons of the last, each reducing the monumental risk bit by bit, and each dependent on technological advances and sustained political and financial will. This is the timeline from dream to descent, a plausible sketch of how the next few decades might unfold. The first phase, already underway, is the reconnaissance phase. We are still identifying and characterizing skylights from orbit. The next generation of Martian orbiters, likely in the late 2020s or early 2030s, will carry more powerful instruments. Think of advanced ground-penetrating radar with finer resolution, specifically designed to map subsurface voids. These missions won't just catalogue holes, they will attempt to trace the outlines of the lava tubes themselves, mapping their length, depth, and structural integrity from space. They will look for clues of ice from orbit, using spectral instruments to detect hydrogen signatures around skylights. This orbital intelligence is crucial for selecting the perfect first target. A skylight that is accessible, leads to a stable-looking tube, and has strong indicators of both scientific value and potential resources. The wrong choice could doom the first daring robotic mission. The second phase, perhaps in the mid to late 20s, is the technological Pathfinder. This is the first mission to attempt a descent. It will be relatively small, focused, and its primary goal will be to prove the entry, communication, and basic survival technologies. It might not be a full-fledged rover. It could be a stationary lander that deploys a tethered probe, a snake, or a small bucket of sensors down into the skylight to capture the first images and atmospheric readings from inside. Or it could be a minimalist rover, designed solely to demonstrate a rappelling descent, survive on the cave floor for a few sols, Martian days, and transmit data back via a relay. The science payload will be secondary. Success here is measured not by groundbreaking discoveries, but by the mere act of getting in, staying alive, and sending data back. This mission will answer the most basic questions. Is our descent method viable? Does our communication relay work through the geometry of the entrance? What are the real-time mechanical challenges of operating in that environment? The data will be a goldmine for engineers, full of unknown unknowns becoming known knowns. Assuming the Pathfinder is a success, the third phase, possibly in the early 40s, would be the first full science mission. This is the rover we've been imagining, a robust, mobile, well-instrumented platform capable of a full scientific assessment. It would descend using the proven method, detach, and begin a methodical exploration of the immediate cavern. Its goals would be comprehensive: detailed geological mapping, atmospheric analysis, a dedicated search for water ice via drills and probes, and the first sensitive hunt for organic molecules and potential biosignatures. This rover would be a mobile laboratory, with the autonomy to make preliminary scientific judgments. It might spend a full Martian year or more inside, slowly expanding its range. The findings from this mission would be transformative, regardless of what it finds. Confirming ice would reshape future human mission planning. Finding any organic material would send astrobiologists into a frenzy. Even finding nothing but pristine, sterile geology would be a profound result, setting boundaries on the possibility of life. The fourth phase, later in the 2040s or early 2050s, would involve more ambitious follow-up. This could mean a rover designed to explore farther, perhaps even traversing hundreds of meters down the lava tube. It could involve deploying multiple robots, a drone for scouting ahead, a rover for detailed sampling, and perhaps stationary monitoring stations left behind to study long-term atmospheric changes. This phase would be about moving from initial exploration to systematic characterization. It would aim to answer: how extensive is this cave network? Are there microclimates in different sections? What is the three-dimensional distribution of ice? The technology by this point would be more mature, allowing for greater risk-taking and more ambitious objectives. Throughout these robotic phases, parallel development for human Mars missions will be ongoing. Agencies and private companies will be working on the heavy lift rockets, life support systems, and surface habitation technologies needed just to get people to Mars and keep them alive on the surface. The robotic cave missions will directly inform this work. If caves with ice are confirmed, The design of the first human outposts will inevitably pivot to leverage those resources. The final, long-term phase is human exploration of the caves themselves. This is unlikely to happen before the mid-century at the very earliest, and more likely later. It will require not just a sustained human presence on the Martian surface, but a significant expansion of that presence. The first human missions to Mars will be short, surface-focused, and fighting for every minute of science and survival. Venturing into a cave will be seen as an extra, high-risk activity. It will only happen once a more permanent base is established, probably on the surface nearby. Then, equipped with the detailed maps and confidence from decades of robotic exploration, a crew might undertake the first human descent. It will be the Martian equivalent of an Apollo mission, an extraordinary expedition into a new realm. They might descend in a pressurized rover via a constructed ramp or elevator, or they might use advanced suits and climbing gear. Their mission would be to do what robots still do poorly: make complex geological judgments, perform intricate sample collection, and conduct the first hands-on search for life. This timeline is not guaranteed. It is a function of funding, political will, and technological breakthroughs. A major failure in an early robotic mission could set the program back by a decade or more. A shift in priorities on Earth could divert resources elsewhere. But the logical progression is clear. Map from orbit, test the descent, do the science, then scale up. Each mission answers practical questions and builds the confidence to ask more ambitious ones. It's a slow, expensive, but ultimately reliable way to peel back the layers of the unknown. The journey to the caves is a marathon, not a sprint. It requires patience and persistence. The scientists and engineers who design the first Pathfinder mission may not live to see the first human set foot in a Martian cavern, but that's the nature of the grandest explorations. They are multi-generational projects. Each mission is a link in a chain, pulling humanity a little further into the future. The timeline is a map of our commitment, showing that we are serious not just about visiting Mars, but about understanding it completely, from its wind-swept plains to its most secret, sheltered depths. Every orbit mapped, every robot lowered, every sensor reading beamed back is a step on that staircase, leading us down into the dark and into a new chapter of history. The step-by-step timeline for exploring the caves of Mars is not just a schedule for one world. It is the prototype, the opening act for a whole new era of solar system exploration. The legacy of those first tentative descents into the Martian dark will extend far beyond the red planet itself, fundamentally changing how we approach other moons and planets. The caves of Mars represent the first test bed, the proving ground for a new frontier that has been hidden in plain sight across our cosmic neighborhood, the subsurface. Think about it. For decades, our exploration has been surface-centric. We land on plains, we roll across deserts, we gaze at craters, but the subsurface has always been the next, great, unexplored dimension. Mars gives us the first realistic chance to develop the tools and strategies to conquer it, and those tools will unlock doors we have only dreamed of opening elsewhere. Consider our own moon. Lunar lava tubes are not just a possibility, they are a certainty. Orbital images show stunning, intact skylights, and the science suggests these tubes could be even more massive and stable than those on Mars, preserved in perfect vacuum for billions of years. The moon's lack of atmosphere means no wind erosion, no dust storms to fill them in. They are pristine time capsules from the moon's volcanic past. And crucially, they offer the same benefits as Martian caves: protection from cosmic radiation, micrometeorites, and extreme temperature swings. The drive to explore Martian caves will directly fuel the ambition to explore lunar ones. In fact, it might happen in parallel or even first, given the Moon's proximity. The technologies we are brainstorming for Mars, autonomous rovers that can descend vertical shafts, communication relays for underground work, power systems for permanent darkness, will be tested and perfected in lunar caves. A lunar cave base is a compelling near-term goal, a place to establish a permanent human presence sheltered from the harsh surface environment. The lessons learned there, just 3 days from Earth, will be directly applicable to the much more distant and challenging caves of Mars. Then, look further out to the icy moons. Europa, orbiting Jupiter, and Enceladus, circling Saturn, are among the most promising places to find life in our solar system. They are not rocky worlds with caves. They are frozen worlds with global subsurface oceans. Europa's icy crust, perhaps tens of kilometers thick, is a barrier separating us from a vast, dark, liquid water ocean. Enceladus actively spews plumes of that ocean into space from cracks in its icy shell. Exploring these subsurface oceans is the ultimate goal. But how do you get there? You must first penetrate the ice. The technologies required: cryobots that can melt or drill through miles of ice, autonomous underwater vehicles that can navigate in total darkness and communicate back through the ice shell. Sensitive instruments to search for biosignatures in the water are the spiritual and technical successors to Martian cave technology. A Martian cave mission is an intermediate difficulty trial run. It involves descending into a dark dot, confined, alien environment, operating with high autonomy, and searching for signs of life in a protected niche. The engineering challenges of communication through a medium, rock instead of ice, power management in darkness, and contamination control are directly analogous. By mastering the exploration of the Martian subsurface, we are building the toolkit for the far more ambitious exploration of oceanic subsurfaces. Every autonomous navigation algorithm refined for a Martian lava tube, every low-power scientific instrument developed to sniff out organics in cave air, every hardy drill designed to sample icy regolith contributes to the portfolio of tech needed for Europa or Enceladus. Furthermore, the scientific philosophy developed on Mars will guide us elsewhere. The careful, methodical search for biosignatures in a cave, distinguishing between biological and geological signals. Understanding the environmental context for potential life will create the protocols and expertise for analyzing a water sample from an alien ocean. The planetary protection protocols hammered out for a potentially life-hosting Martian cave will become the gold standard for exploring an ocean world where the chance of life is considered high. The journey to the Martian caves is therefore a training mission for the entire outer solar system. It moves our exploration paradigm from two-dimensional surface study to three-dimensional subsurface investigation. It acknowledges that the most habitable real estate in our solar system may not be on the surface, but beneath it. This shift is monumental. It means our future probes and landers will be designed not just to sit on a surface, but to penetrate it. It means our understanding of habitability will be forever tied to the concept of subsurface refugees. The legacy of the first Martian cave mission will be a blueprint titled How to Explore a Hidden World. This blueprint will have chapters on access, on survival in darkness, on autonomous science, and on the ethical exploration of potential biospheres. That document will be as valuable as any rocket engine. It will enable a future where we don't just fly by or orbit icy moons, but where we send probes that burrow into their crusts and release submersibles into their dark seas. It will enable a future where lunar colonies thrive in the permanent, stable environments of lava tubes, using them as natural foundations for cities. The caves of Mars are the first domino. Their exploration sets off a chain reaction. The technology, the confidence, and the scientific knowledge cascade outward. The struggle to lower a robot into that Martian pit will be remembered not as an isolated stunt, but as the birth of subsurface planetary science. The scientists and engineers who solve those problems will be the ones we task with designing the cryobot for Europa. The companies that build the tough, flexible rovers will be the ones contracted to build the excavators for lunar cave bases. This is how exploration evolves. It builds on itself. The Martian caves are the perfect next challenge because they sit at the intersection of known engineering and profound unknown. They are hard, but not impossibly hard. They offer a clear, compelling reason to go. And by conquering them, we don't just learn about Mars. We unlock a skill set that becomes part of our species' capabilities. We become the creatures who can explore not just the face of a world, but its heart. So, when we finally see that first grainy image from inside a Martian lava tube, it won't just be a picture of another planet's interior. It will be a picture of a new path forward. It will be a glimpse of the future of humanity in space, a future where we are no longer surface dwellers confined to the skin of worlds, but subterranean explorers, capable of seeking out life and building homes in the most sheltered places the cosmos has to offer. The journey to the mysterious caves of Mars is, therefore, the beginning of a much longer, deeper journey. It is our first concerted step into the inner space of other worlds, a declaration that we are ready to look beneath the surface, literally and figuratively, to uncover the full story of our solar system and find our place within it. That is the true legacy, a shift in mindset, a new toolkit, and an open road that leads from the dry, cold caves of Mars to the icy shells of distant moons and beyond, forever expanding the boundaries of where we can go and what we can discover.